For decades, astronomers have been searching for one thing beyond our galaxy: chemical fingerprints that could hint at the universal recipe for life. Now, the James Webb Space Telescope may have finally found them. Using its powerful infrared instruments, JWST has detected complex organic molecules, the same carbon-based compounds that form the foundation of life outside the Milky Way. That discovery doesn't just expand our map of chemistry. It challenges what we thought was possible about where and how life could begin. The finding came from Webb's deep look at a small, faint galaxy roughly 12 million light-years away, a place so distant that even Hubble could barely resolve its structure. But with JWST's mid-infrared instrument, MIRI, astronomers could see the subtle chemical glow that dust and molecules emit in infrared light. And inside that glow, they found a distinct set of signatures, patterns in the wavelengths that match polycyclic aromatic hydrocarbons, or PAHs. PAHs are complex, ring-shaped molecules made of carbon and hydrogen, and they're important for one reason. They're the building blocks of prebiotic chemistry. On Earth, compounds like these form naturally in everything from smoke to meteorites, and they can evolve into amino acids and nucleotides under the right conditions. Detecting them outside our own galaxy means the same chemistry that seeds life here might be happening everywhere. To understand how profound this is, consider what JWST actually saw. The telescope didn't find a single molecule floating in isolation. It saw broad infrared emission bands between 6 and 12 microns, the exact wavelengths produced when PAHs vibrate under ultraviolet light. These signals were scattered throughout a region of a dwarf galaxy known for active star formation. That's crucial because dwarf galaxies are chemically primitive. They have far fewer heavy elements than the Milky Way. Conventional wisdom said PAHs couldn't easily survive there. They'd be destroyed by radiation or never form at all. And yet, there they were, glowing faintly through the dust, thriving in an environment we thought was too harsh for them. That means something remarkable. Organic chemistry doesn't need a metal-rich galaxy like ours to get started. It can arise even in the simplest, most ancient corners of the universe. To grasp how unexpected that is, we have to go back to what astronomers mean by metals. In cosmic terms, anything heavier than helium counts as a metal: carbon, nitrogen, oxygen, iron. These elements are forged inside stars and spread when those stars die. Early galaxies, born soon after the Big Bang, didn't have many of them. So for decades, scientists assumed early galaxies couldn't form complex organics. They simply lacked the raw material. JWST is proving that wrong. Its extreme sensitivity allows it to detect faint, mid-infrared spectra even in galaxies billions of times dimmer than our own. And the data shows that carbon-based chemistry is everywhere, even in low metallicity systems. The universe, it seems, doesn't wait for perfect conditions to make complexity. It just gets started. But how do these molecules form in such environments? The leading theory involves carbon-rich dust grains expelled from dying stars. When ultraviolet light from newborn stars strikes these grains, it triggers chemical reactions on their surfaces, assembling carbon rings that eventually become PAHs. In the Milky Way, this process is common. Seeing it beyond our galaxy confirms it's a universal mechanism, one that operates no matter how far from home we look. What makes Webb's discovery so important is what it implies for astrobiology. If PAHs can form and persist in distant galaxies with little metal and intense radiation, then the universe is likely full of chemical starter kits for life. These compounds can travel on interstellar dust, freeze onto comets, and eventually find their way to planets, perhaps even alien worlds orbiting other suns in those same galaxies. In other words, the chemistry of life isn't unique to Earth or even to the Milky Way. It's cosmic. It also changes how we think about the timeline of life's potential origins. For years, scientists debated whether complex organics could have existed early in the universe when the first galaxies were young and chaotic. JWST's findings suggest they did, meaning that even within the first few billion years after the Big Bang, the basic ingredients of biology were already forming. Life, at least in chemical potential, may have had a head start on a cosmic scale. To make sure this signal was real, researchers compared Webb's infrared data with models and with local analogs, nearby galaxies whose dust and star formation properties are well understood. The match was exact. The same distinctive PAH bands we see in our own Milky Way's nebulae are present in this distant dwarf galaxy. And in some ways, they're even stronger, perhaps due to different dust grain sizes or a harder radiation field. There's something poetic about that. These tiny molecules, shaped in the furnace of ancient stars, are emitting their faint light across 12 million years of space and time, and we're only now able to read their chemical signature. Every carbon ring Webb detects is a message from a galaxy that existed long before our species began wondering where we came from. What does this really mean for the bigger picture? It means that the chemistry of life is not rare. It's not a fluke of our solar system or even our galaxy. The processes that built the organic scaffolding for life are built into the universe itself, woven into the way dust and light interact wherever stars are born and die. That's the part that gives scientists chills. Because if the same chemistry repeats everywhere, then the odds that some of those places took the next step, forming amino acids, proteins, maybe even primitive cells, just went up dramatically. There's also a practical side. By studying PAHs outside the Milky Way, astronomers can trace how carbon evolves across cosmic time. PAHs absorb and emit light differently depending on their size, structure, and charge, so they act as chemical thermometers for the environments they inhabit. By mapping them in other galaxies, Webb can tell us how star formation, radiation, and metallicity influence the evolution of organic material. It's like tracking the life cycle of carbon across the universe. Some researchers are already calling this galactic biochemistry. It doesn't mean there's life out there, but it does mean the preconditions are far more universal than we thought. The same molecular fingerprints that give birth to life on Earth could be lighting up star-forming regions in galaxies millions of light years away. And this is just the beginning. JWST's instruments are now powerful enough to detect even subtler signals, complex organics with nitrogen, oxygen, or sulfur bonds, which are even closer to biological molecules. Future observations could reveal whether these compounds exist in abundance across galaxies or whether the one we've seen is an exception. If they're common, it would mean that the universe is chemically primed for life at every scale. What makes this discovery resonate beyond the science is its simplicity. For all its billion-dollar precision and golden mirrors, JWST is doing what humanity has always done, looking outward to understand ourselves. When it detects carbon rings glowing in a galaxy 12 million light-years away, it's not just seeing molecules. It's seeing the same chemistry that once gave rise to oceans, DNA, and consciousness here at home. So what does it really mean that JWST found complex organics outside the Milky Way? It means the universe is writing the same story everywhere, a story of carbon, light, and time. It means that life's first spark wasn't confined to a single world or even a single galaxy. And it means that when we look out into the dark, we're not just seeing stars. We're seeing the raw ingredients of life itself, scattered across the cosmos, waiting to begin again.